To introduce tonight's speaker, Helene Intraub, member of the governing board, will perform those honors.
Unfortunately, I have to log back on. Okay, that's a little bit better. I want to thank my colleagues on the governing board for giving me the great honor of introducing the 2011 keynote speaker, Nora Newcombe. Nora is a professor of psychology and James H. Glacken Distinguished Faculty Fellow at Temple University. She is also the PI and director of the NSF Spatial Intelligence and Learning Center, affectionately referred to as SILC by most of us. This is a consortium of universities, numerous researchers in various fields that are encouraged to work together to understand spatial intelligence. The other mission of the center is to do translational research and to take from basic cognitive studies, ideas for going to the classroom, for maybe coming up with new educational tools to help young kids get on the way to understanding STEM science. Nora has received numerous awards over the years. I've just picked out a few from APA, such as the George A. Miller Award, the G. Stanley Hall Award, the Award for Distinguished Service to Psychological Science. She's also held many editorial positions, and they tend to represent a very broad approach, which is sort of the truth about Nora and her work. When she was editor, it was of JEP General, associate editor, Psychological Bulletin. She's currently associate editor for Wiley Interdisciplinary Reviews, Cognitive Science, and action editor on cognitive psychology. She also has a tremendous commitment to leadership in professional societies, and there are, again, so many examples. I'll just talk right now about one in APA. She is currently the chair of the Board of Scientific Affairs, and in fact, she won't even get to rest after her keynote. She kind of has to pack, jump on a plane, and chair a conference in this very important venue. She has also been the past president of Eastern Psychological Association, member of the Psychonomic Governing Board, and there is just a huge list. Her research is motivated by fundamental philosophical questions about the mind, spatial representation, and the acquisition of knowledge. What always strikes me when I read one of Nora's papers is that you're reading some interesting experiment, you're getting into the details of a clever study, but you never lose sight of the big picture, because she never loses sight of the big picture, and makes that clear in everything that she writes. Her specific areas of focus are in the development of spatial cognition. You'll see a number of wonderful examples today. Also, individual differences in spatial ability and the potential role of training, autobiographical memory, and the all-important translational applications of this research. All of this work has led to over 150 publications and counting, and this includes 5 books. One of these is a major cornerstone book in the area of spatial cognition, co-authored with Jane Ellen Huttenlocher, and that's Making Space, the Development of Spatial Representation and Reasoning. That is such a high-impact book over the past 10+ years, and is likely to be so for years to come. In terms of her translational work, I'd like to say that not only is there ongoing research at SILC, but Nora does what we all need to learn to do better, and that is how to take the science that we do and talk about it to people who are not also psychological scientists, but people out there in the world, people in education, parents, people raising kids. And in 2010, she had a wonderful article that I recommend you take a look at in American Educator for teachers. It's called Picture This: Increasing Math and Science Learning by Improving Spatial Thinking. And if you take a look at it, it's a beautiful example of not just talking the talk in a grant application about your translational work, but actually walking the walk. And some of her ideas about spatial cognition and STEM science learning was featured in a recent article in Science Magazine. In addition to all of this publication and all of this service to the science community. Nora is also a wonderful mentor, not only within her own lab, but across labs, universities, different areas. And this was marked in 2006 by a Women in Cognitive Science Mentorship Award, certainly well deserved. And so it's with great pleasure that I ask everybody to give Nora a warm welcome and tell us. I think we're supposed to have her first slide up. They still have us up.
That's great. Thanks so much. Thanks. So it's an incredible honor to be here, and I'm very aware that this is an audience that integrates across a bunch of fields, but normally does not include very many people who study development. There's a few in the audience, but it's not a big group. But what I hope to do today is to exemplify something that I feel very passionate about, which is that the integrated study of the human mind and brain needs a developmental approach, a cognitive approach, a neural approach, can learn from comparative psychology, and that this is really one of the sort of purposes, in my mind, of the Psychonomic Society, is to really bring together these different kinds of perspectives. So I did think to start, though, with mentioning the question of why study development, since I know a lot of you don't. And I think there are big reasons, too, one of which is that understanding development can constrain our models of mature functioning. So you shouldn't really posit a model that you can't grow. I realize that's not always a constraint that's imposed, but to my mind, it's an important one. A second one is, and this is really going to be, I think, the one that I most focus on in this talk, is that asking questions about development allows us to consider really key questions about human nature that have preoccupied philosophers from thousands and hundreds of years ago, and that still really, I think, for me at least, motivate the study of cognitive science. And then a third, which Helene mentioned quite a lot, but which I'm not going to talk about tonight, is that understanding a certain domain, in this case spatial skills and spatial learning, can help us to improve education. But I can't do everything in one talk, so I'm not going to address that, but it's something to keep in the back of your mind. So the structure of the talk really revolves around the idea that there are various kinds of theories of development. And in my mind, in a very sort of simple way, they can be defined in terms of whether they posit weak starting points or strong starting points for development in the sort of equipment that human newborns bring to the task of understanding the world. And also whether they posit a weak mature state that we all get to, or a strong mature state that we all get to. Now, one of these cells where you start strong and end up weak doesn't make a lot of sense. And in thinking about how to sort of fill this cell, the best person I could come up with is Jean-Jacques Rousseau. And that's kind of cheating because he wasn't really talking about cognition. He was talking about, you know, people are born, kids are born sort of innocent and wonderful, and they're sort of corrupted by society. And that's a whole sort of different dimension of thinking. But if we cross out the upper right and just sort of say, okay, let's forget about that one, then what you'll see is that the bottom row in this 2x2 is really what is, this defines the classic nativist empiricist debate. So John Locke and the other empiricists thought that kids started weak and ended up strong. And Immanuel Kant and many nativists after him thought that kids started out strong and ended up strong. And that's kind of an oversimplification, perhaps, but it's what it amounts to. But you might be thinking, well, what about that upper left? And this is where I think in modern cognitive science, there's been a kind of wrinkle thrown in the debate about nativism and empiricism, in that there are many people who doubt how strong the ending point is. So there's a lot of debate about how rational adults are and what sorts of cognitive biases we might all be subject to. And of course, for a developmentalist, you need to know where you're headed before you really know what the task is of how to get there. So the plan of today's talk is that I want to talk a little bit about why I'm going to play this out with regard to the domain of space, just justify that briefly and give you a little vocabulary. But then I'm going to talk about whether the mature state is weak or strong. So what do we think of that upper left corner? And what I'm going to argue is that we can rule that one out. This has to do with the debate over whether or not there's a cognitive map and so on and so forth. So how strong is spatial functioning in the human adult? Then having done that, the second, or I'm counting Y space as sort of a preamble, the second of the three major parts of the talk has to do with the nativist empiricist debate. So I'm going to review the debate that has existed and is still raging over whether or not there's a geometric module, which is one instantiation of this debate. And then I'm going to, having in my own mind established the relevance of not exactly the lower left, because I think that no one these days is a blank slater. So what I want to do eventually is to redefine weak starting points to be experience expectant, strong starting points of a certain kind, and then to say how we can sort of flesh out that lower left corner in modern terms. So going to Y space, the preamble, there are many cognitive domains, and many of you study them. You study language, categories, causality, theory of mind, number, and they're all wonderful, and I enjoy them, and they're worth talking about. But I have spent much of my life, occasionally I've studied episodic memory, but I've studied for much of my life I've studied space. And I think the reasons for that, are several. In an evolutionary context, spatial adaptation is vital. And this is where you can, I think, easily bring in the comparative cognition perspective. And if anyone was at the comparative cognition sessions earlier today, you know very well that any mobile animal has to be able to find food, find mates, find its home, avoid predators. And so from this point of view, the problem of navigation, the problem of finding your way in the wider world, is a ubiquitous, pervasive, vital one for survival, for humans, but also for other mobile animals. Now, it's also true for humans that we use tools, and we can get into an argument about how exactly species-specific this is, but it's certainly a very distinctive aspect of the human species. And making and using tools is also a kind of spatial adaptation. So that's the evolutionary context, and in modern life, this continues. So we still, have to find our way. We augment that with certain kinds of signs and devices. We still have to use tools to assemble furniture, and then there's the whole science, technology, engineering, and math STEM angle that Helene mentioned, where, interpreting graphs, imagining molecules, figuring out angular momentum, all those kinds of things are fundamentally spatial. So I think it is an important domain. And it's been divided, as I hinted at already, between what I think are two really quite different kinds of interest in space. One has to do with navigation, finding your way around in the world, and the other has to do with these basically tool-centered kinds of thought, which are centered on objects. And when those are transformed, they involve processes like mental rotation. I'm not today going to talk much about the second kind of process, although I think it's very interesting and very important. I'm going to concentrate on the study of navigation. So I think there are contrasts between the two at the behavioral level, at the neural level. I think it's quite interesting how they're both spatial and yet they're different, and how do they relate to each other. But I'm really not going to develop that. I'm going to talk about navigation. So when we consider navigation, I just wanted to quickly introduce a little bit of terminology for those of you who don't work in this domain, which every once in a while I'll use. Keeping track of where you are in the world and planning how to get around in it can be done either with respect to yourself, egocentrically, or with respect to other things in the world, allocentrically. Now, egocentric learning has kind of a bad reputation because people think of it as just being response learning. So just being, I do this and I find something, or I walk a certain distance and turn right and I find something. And that's all very well, but it doesn't work. If you change your start point, then you have to walk ahead and turn left, not turn right. And if you move, then you can't do this and find your cup of coffee. So it's a really limited form, but dead reckoning, which is also called inertial navigation, is a form of egocentric coding in which you remember how far you've gone and how much you've turned, and you correct your view of the world for those kinds of changes. Now, it is a great system. Its problem is that error accumulates. So every time you think you turn 60 degrees, but really you only turn 55, and et cetera, that really adds up. And actually, dead reckoning is sometimes thought, this may or may not be true, but it's sometimes thought to be called dead reckoning because if you're on the open ocean using dead reckoning, you could end up dead because you miss the island that you could get water at or something like that. Now, allocentric systems also come in two varieties. One of them, Q learning, or sometimes it's called beacon use, also is kind of not spatial. It's basically associative learning. So if you remember that you buried the treasure, under the rose bush, right in front of the church, then you don't really have to remember where it was, you just have to look for the rose bush. So it can help you function in the spatial world, but it's really fundamentally associative. But place learning is probably the most reliable system we have, in which we use distal landmarks that are far off that allow you to basically triangulate the location of something by the distance and direction from those various kinds of landmarks. So that's it for the preamble. We're on to the first of the three sort of major parts of the talk, where I wanted to talk about whether the mature state is weak or strong, and in particular the debate about whether human adults do form cognitive maps. Now, of course, this is an old idea. All of you probably remember that it was proposed by Tolman, and that the hippocampus is cognitive map by O'Keefe and Nadell proposed this idea in its very title. And there's many other works that have used what essentially is a metaphor about the spatial world. But this idea has been questioned in the minds of many by findings of biases and findings of distortion in human spatial judgments. And one of these kinds of findings concerns asymmetries. So for a lot of people, the following fact is really problematic for the notion that human beings are very rational in the spatial domain, which is that you can find that people will judge the distance from point A to point B, and then judge the distance from point B to point A, and that those judgments will not agree, that they won't be equal. And this has been found in a wide variety of kinds of settings. Now, it doesn't happen if you just say point A to point B and then point B to point A, because people kind of know that it was supposed to be the same, so they'll say the same number. But if you space it out and this kind of thing, they really will give you very different estimates. So people have argued that this means that space is at least partially non-Euclidean, or perhaps consists only of associative links. And I think this is not the case, and to explain why not, I have to back up just a little bit and brief you in another aspect of the way that people have described the spatial world, which was originated by Jane Ellen Huttenlocher and Larry Hedges and their colleagues, and in particular for spatial coding in this paper from Psych Review 1991 by Huttenlocher, Hedges, and Duncan. So the idea is that people remember both the general category of where something is. So in the case of a dot in a circle, which a lot of their experiments concern dots in circles, they remember that it's in the upper left or the lower right. They basically turn out to divide the circle into quadrants, and they remember that a particular dot was in a particular quadrant. In addition, they remember in some fine-grained or quantitative or coordinate or metric, there's a lot of sort of more or less synonymous terms here. And it turns out for the circle that people actually use polar coordinates. But they remember in some kind of metric way where a particular dot was located. Now, their metric memory sort of is uncertain, and it tends to erode over time, and it leaves behind the categorical memory. So the categorical memory is used to sort of correct or adjust the increasingly imprecise quantitative memory, and that creates bias towards the sort of mean value, or in this case, the sort of gravitational center of those quadrants. So there is no underlying distortion. There just is uncertainty and correction by categories, but that creates bias. Now, you might be saying dots and circles, well, okay, but that's not really the real world. More recently, Mark Holden and a group of us have shown that this is also true for remembering locations in 2D images of the natural world, and even more recently, Mark Holden in his dissertation has shown that it's true for people walking around in the actual 3D world. So it's, I think, an interesting framework from which to approach the idea of how we think about asymmetries, which we did in this paper from this point over a decade ago. And what people did in this experiment was to learn a whole variety of locations in this quote-unquote map. It's kind of a rotten map, right? They learned these locations, but I know you can't see this. So what I've done is to kind of blow up just a quadrant of the map. So in each quadrant, there's a location that is indicated with a star and is presented in capital letters, and it's sort of the prototype, if you will, of the quadrant. And then there's 4 other points that you learn. And having learned these points to criterion, you're asked to estimate certain distances. And I think the arrows kind of, for me, tell the whole story. The fountain is closer to the museum. So if you fix the fountain and you say, how far is it from the fountain to the flag is then going to move quite a lot, because the flag is far or further from the museum. So it'll be a shorter distance. Whereas if you fix the flag and you say, how far is it from the flag to the fountain is close to the prototype, and it's not going to move much at all, and so it's going to be a longer distance. So what you end up is an asymmetry, but it's predicted from this theory that's hierarchical, in which at the fine-grained level, there aren't really distortions. So from that point of view, I think that although asymmetries are very interesting and very important, they, for me, don't question the sort of essential, sensible nature of human spatial representation. Now, you might say, well, that's all very well, but you promised me you were going to talk about cognitive maps, and that's not really a cognitive map, that's some sort of, other phenomenon. So I wanted to address head-on the issue of cognitive maps and build on what I think is a really interesting paper by Ishikawa and Montello in Cognitive Psychology a few years back, in which they suggested that the answer to this question actually was one that involved individual differences. So some people are really good, some people are not so good, but they learn, and some people don't really learn. So basically, there are cognitive maps, but only for some people. It's a matter of individual differences. It's an interesting kind of answer. They based this conclusion on an experiment in which UC Santa Barbara undergraduates were driven around these sort of ritzy areas above Santa Barbara that they never usually went to, and they followed either one of 2 routes, an S-shaped route or a U-shaped route that didn't intersect with each other. You can vaguely see those on the map. And then at some point, they were driven along a connecting route. And they were asked to make pointing judgments. And the really good people were able to point from one route to another immediately. The not so good people learned over time to point from one route to another pretty well. And the people who never learned had no idea where they were ever. So we thought this was interesting, but we were worried that they were passengers in a car, and we know that passive spatial learning is not so good. And we also worried that there was only one connecting route, and one connecting route is not so many. It doesn't really fix the relationship between the 2 routes. Is not that well fixed by the one connecting route. So we did a very similar experiment on a campus that Temple University has in a town called Ambler that most Temple students never go to. So it was a novel environment. We had them walk the route that you see at the bottom in blue. We had them also walk the route that you see at the top in gold. They were taken between the two in a wheelchair, blindfolded, and wearing headphones while listening to music. So that's how they did not see the relationship between these two routes. It's important to know that Victor Shinazi and Dan Nardi are kind of, able to push large people in wheelchairs. This was an experiment that took a certain amount of muscle. And then on subsequent days, they experienced first one connecting route, the green one or the red one, and counterbalanced, and then the other one. So the essential results are here. The bottom line, the brown line, is the within route pointing. Now, people are not ballistic in their pointing. They never get that much better than about 30, 35 degrees. They're a little off, So that's kind of the baseline of how well you can do in most of these kinds of tasks. The green line shows how good they are at pointing from a location on one route to a location on the other route. So there's two things to note in this graph. One is that subjects show a significant improvement after experiencing the first connecting route. So even at session 2, let alone at session 3, it turned out we were wrong. One connecting route is enough. So by session 2, the between route is as good as the within route, and the individual differences aren't really there. Everyone is really able to integrate the two routes in this situation in which they are actively moving around in the world. The element where you do see some individual differences is in the first session, where there's a lot of variability. There's an enormous bar around the green dot in the first session. And that's because some people didn't have a clue before experiencing the connecting route, and some people were able to do the task pretty well even without experiencing the connecting route. Now, you might say, how is that even possible? And the answer is that there's many cues that you could use. We couldn't control whether or not the sun was out, so you can control the sun, or you can use the sun. We couldn't control the fact that there's topography to this, so this is actually slanted upward, and this is flat, so there's a limit to how the slanty part could be related to this, the flat part. There's actually a common building in there which looks really different from the back from the front, but if you're alert, you can tell that they're the same building. So some people are good at noticing these things and some people are not, and yet I think one big message is that they can integrate across, and even the bad people can integrate by the time they've experienced a connecting route. So I won't tell you about some findings that we have that relate how good you are in that first session to actual structural differences. Those people have a larger hippocampus, just to tell you the punchline, just like those London taxi drivers. And there's also some functional differences on fMRI. But the major conclusion to the first part of the talk, and this is glossing over, I know there could be much more debate, but the major conclusion I want to draw is that there is a strong mature state for navigation, that asymmetries don't indicate fragmented or associative spatial relations, and that human adults, at least in some circumstances, can form cognitive maps. So given that, the question becomes, how do we get there? And that means addressing squarely the nativist empiricist debate. So we've ruled out not only poor Jean-Jacques Rousseau, but also, at this point, I recognize I've done it quickly, but ruled out the upper left. And in developmental, Liz Spelke has been a very active proponent for this domain as well as for other domains of the idea that there are innate starting points as well as a strong mature state. And this raises not only the issue of nativism versus empiricism, it raises a couple of other theoretical issues too, which I wanted to highlight for you. One is whether or not the mind is modular, because the specific hypothesis that she's advanced is that there is a geometric module that is innate, and this, for some people, fits with a sort of evolutionary approach in which adaptive pressure selects specific modules. That's the entity on which evolution operates. Now, the other thing that comes in here is the perennial language and thought problem, because there actually is some development in the operation of the geometric module, as I'm going to show you in just a second. And for someone who believes in innate starting points, it's sort of a problem if there's development, because why is there development if you're starting from these very strong starting points? And for Liz, the answer has been that human language serves to integrate and to enrich the geometric modules. So the language and thought problem comes in here. So I want to say that the Spelke position is not massive modularity. So there are people in the world who think that everything is modular and innate modules have proliferated, including to, theory of mind, face processing, cheater detection, and so forth. The geometric module is then but one of many, many modules. Instead, the position is one called the core knowledge perspective, in which geometric relations is just one of a mere 5 domains that have these kind of innate starting points. So I won't have anything to say about the other ones, but I just want to say that it is a limited list. I also wanted to say a little bit about what we mean by modularity here, because I know a lot of people use the term module or modularity in a lot of different ways. And what we don't mean is neural specialization. There surely are neurally specialized areas for certain kinds of functions, but to the extent that those different kinds of neural processes end up integrated or talking to each other in such a way as to underlie behavior, then I think we're not talking about the specific controversy here, which has to do with what Fodor in 1983 specified as a module being not only hardwired, that is to say innate, but autonomous. And sometimes people use the term encapsulated or the term impenetrable, and they cite the example of the Mueller-Lyer illusion. So no matter how much you look at those horizontal lines, you can't make yourself see them as equal. Your perceptual system is encapsulated in such a way that your cognitive system or your linguistic system can't penetrate it. You can say as much as you like, they are equal, they are equal, they are equal, and you look at it and they don't look equal. So that's at least one example of impenetrability. The issue is how many such examples are there out there, and is it a sort of widespread principle of the human mind-brain? So the geometric module, I think, is best defined by really discussing the paradigm that people have used to look at it. It was first devised by Ken Cheng in 1986 in his doctoral dissertation at Penn using rats. The lower left is a picture that Ken took, which is not of a rat. It's of a little stuffed, looks more like a mouse than a rat to me. But he said it was hard to take a picture of the rats because the rats didn't know to stay still for their picture. So that's his picture. And then the apparatus at the right is the one we've been using. But the basic idea is that there's a rectangular enclosure. There are 4 hiding places in each of the corners. For rats and other animals, you typically hide food. For human children, who, heaven forbid, you should hide food. They might be allergic, or their parents would get upset. We hide little toys. And then they're disoriented. The animals or the human children are disoriented by being spun around. The rats you put in a box and spin it. The human children, you hold your hands over their eyes and move them around. Sometimes you sing Ring Around the Rosie. There are differences between species and how you disorient them. But the basic idea is that you're disengaging that inertial navigation or dead reckoning system that I talked about earlier, concentrating on the allocentric system and how it's used in reorientation. And there are 2 kinds of information that are contrasted. One is the geometric information, which is the length and the length of the long side, the length of the short side, and their ratio. So in the all-white room at the left, There's a toy, say, hidden where the long side is to the left of the short side. Once you're disoriented, there is no way to tell the C corner for correct from the R corner for rotation or reversal. And indeed, the children who are 18 to 24 months evenly divide their search between those two corners, as did Ken Chang's rats. So these toddlers are behaving just like the rats did. And, you know, they're toddlers. Some of the time they go to the wrong corners, the far error, the near error. But the main thing is that they're evenly dividing their errors. Now, this is definitely something that happens. I have no quarrel with this finding. Using the length relationships is true. It's a really striking finding. What I think is problematic is the finding that's shown at the right, which is that when you add a colored wall, thereby making it pretty easy, you would think, to go to the correct corner. It's the one where the long wall is to the left of the short colored wall. The children didn't do that. And in fact, this particular data set, it even looked like they went more to the reversal corner, but basically they still do a 50-50 split. So why is it that they're ignoring the colored wall? That's the impenetrability finding, and that's the basis on which the claim of the geometric module is made. Now, you're all adults, and you have a strong, mature state, so you're probably thinking, well, I wouldn't do that, and in fact, you wouldn't do that. So in experiments with adults, in this case, there were 96% responses to the correct corner. It's almost always above 90%. You have to wonder about those undergraduates who don't go to the correct corner, like, what is wrong with them? But, you know, it's over 90%, so they're doing pretty well. So this is where, as I said, the language hypothesis comes in. If there's this transition between toddlers and human adults, how does it happen? In particular, it happens at the age of 6, and what Spelke and her group have argued is that it's linked to the productive control of the terms left and right, that you need those terms in order to put together the blueness or the redness or whatever of the colored wall with the length relationships to integrate those two. So there is support for this approach. There's the transition at 6 years, which turns out to be correlated with productive, not passive comprehension, but productive use of the term left and right. Anna Schusterman has found that if you train 4-year-olds to be able to use the term left and right, that they do better, that they do go to the correct corner. And it's also been reported that if you make adults do a linguistic shadowing task, you can make them become like children. You find that they still use the geometry, but they fail at this point to use the colored wall information. So it's a pretty impressive set of findings, but I think that language does not play a necessary role, and I'm going to give you 3 arguments for that, and then I'm going to swing into some other arguments about the geometric module. So first of all, non-human and non-linguistic animals turn out to be able to use features. Secondly, young children can use features in larger rooms. And thirdly, human adults' feature use can be disrupted by spatial shadowing as well as by verbal interference, verbal shadowing. So there's a list of species here. The figure is taken from work with monkeys where you probably can't see it, but with the colored wall cue, they go 75% of the time to the correct corner. And that has also been found for chickens, for pigeons, and for the definitively non-linguistic animal, the fish. So you might say, oh, well, you can stop here. I mean, if non-linguistic animals can do this, it couldn't have anything to do with language. But the problem with that, and this is a sort of reply that Spelke has made, is that indeed you can do it, but it takes hundreds and hundreds of trials. So it's not necessarily the same thing as when you can rapidly and flexibly see exactly where the correct corner is. But it turns out that featural cues are only neglected by human children in really small rooms. So what I haven't told you so far is that the room that Spelke and her colleagues use is only 4 feet by 6 feet. It's a really small room. In fact, a colleague of mine who went in it at one point had to leave quickly because when she's afflicted by claustrophobia. She said she really couldn't stay in it. So what we used instead was an 8 by 12 room, which is 4 times the square footage, but has the same relationship of the long to the short. And what this graph shows is 0 doesn't mean you're at chance. 0 means you're using the geometry, but it's an index of whether or not you're using the features. Whoa. And in the larger room, you can see that you're way above 0, even as a toddler, although you do get a bit better with age. Whereas in the small room, you have the pattern of findings that I've mentioned so far, which is the transition at 6 years. Now, the question arises, which is the special case? Is the small room the special case, or is the large room the special case? My argument would be that the large room is more a sampling of the real world that spatial adaptation occurs in, which after all is a lot bigger than 8 by 12. In fact, it's a big, big world out there. So the small room is the special case, and I'll have a little bit more to say about that in a minute. So the last point in terms of the language and thought aspect of this problem is that spatial shadowing, as well as verbal shadowing, reduces feature use in adults. So we did the verbal shadowing thing. We were able to replicate the finding, which is not shown. Those data are not shown. We didn't get the adults quite back to the 50-50 split, but they got way worse. So they were down in the sort of 50% versus 30% that you see here also for the spatial shadowing. So the spatial shadowing was adapted from Lee Brooks' old task from the 60s. You had to imagine these block letters and go around the vertices and say which ones, say yes, 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 no, no, etc. You say yes if they're if the vertices are on the top or the bottom line that the capital F is on. So when you're doing this, having to imagine the capital F and keep track of where you are, it's a pretty spatial challenging task, and it gets adults down to 52% correct, which is significantly better than 33%, but still pretty bad and equivalent to what happens with verbal shadowing. So I think it's a more general problem than just the linguistic shadowing. So turning away from the language and thought part of the talk, what I want to argue, and which is more germane, I think, to the nativist empiricist question, is that experience matters. So your ability to use features develops both in the short time of experiment and also over the sort of developmental time of rearing. Within an experiment, what we did in this study with 3-year-olds was first give them a few trials, 4 trials in the larger room where we knew they could succeed, and that's the green bars. So the green bar at the left is the correct corner. The next green bar is the rotation corner, and you can see that the correct corner is beating the rotation corner. And then there's the near and the far errors, because they're little kids, so they always sometimes go to the completely wrong corners. And then we put them in the small room, where normally they can't succeed, after just the 4 trials in the larger room. And in the smaller room, in the red bars, they're using the feature. In fact, if anything, they're using the feature more, but of course they had the practice in the larger room. So it really only takes the 4 trials to sort of alert them to the usefulness of the feature. And there's a very similar, although based on a different paradigm, but a very similar finding in Twyman, Spetch, and Friedman. So it's there, it's lurking, you just have to bring it out. In the rearing environment, you can also look for the effects of the sorts of spatial cues that have proved useful. So we bring up our children in the built environment. They're in cribs, in rooms, which are rectangular. We raise our lab animals in cages, which are rectangular, which have geometry. So they have much experience with geometry. And the question is whether the experience with geometry is relevant to the ubiquitous appearance of this kind of, spatial cue. Now, when I bring this up, people often suggest that I go and study children being raised in igloos or yurts or other such things, but I'm not convinced that anyone would fund me to do that. I'm also not convinced that anyone is still really brought up only in an igloo or only in a yurt. So instead, what people have done is to turn to work with non-human animals, since it's difficult to control the rearing conditions of humans. And a lot of this work has been done in Marcia Speccia's lab at Alberta, working with 2 different kinds of chickadees and also with fish. And then Valortagara in Italy has been working with domestic chicks. And the data are divided. So there's some evidence of fairly rigid development in the domestic chicks and also in one of the kinds of chickadees, and of more malleable development in a different kind of chickadee and in fish. So what we thought is, well, at least we should try a mammal. And what we were able to do is to use mice, because a colleague of mine has a mouse lab. And we reared little mice in circular enclosures for 2 months, which were featurally enriched. So half of this circle is painted blue and half of this circle is painted white. And the mice were the other group of mice were reared in rectangles for 2 months, which you could argue is geometrically enriched, although it's similar to what we normally rear the mice in. They're, by the way, reared with their moms, because otherwise they would die. So we also have a little bit of a housing experiment. And even the housing had a bit of an impact, but I'm mainly going to tell you the rearing data. So once they're 2 months old, we put them into a training regime in a rectangular enclosure where there are distinctive, so this is not the colored wall paradigm. It's a similar paradigm that actually was used originally by Ken Chang, in which there are distinctive cues. The cue learning is happening in each of the different 4 corners. And so the first finding is that the mice reared in the circle were able to learn to use the cues more quickly than the mice that were raised in the rectangles. Now, these mice, I'm kind of amazed it takes this long. Like 171 trials is significantly shorter than 224 trials. You know, I'd never done work with non-human animals before, but anyway, it takes the mice a while, but the ones that are reared in the circle learn quicker. But the really important finding isn't that we can enhance featural use, although I think that's interesting. The really important finding is that we get different results for use of geometry. So having run them in this training paradigm with the cue learning, the question is whether they learned anything about the geometry. When you take the cues away, do they know that the correct corner is where the long wall is to the left of the short wall, or not? If they do know that, then they should be able, they won't go always to the correct corner, but they should concentrate on the 2 geometrically correct corners. So they should be better than 50%. And the rectangular reared mice are better than 50%. They're 75% at going to the 2 geometrically correct corners. But the circular reared mice don't beat chance. They're at 53%. They don't use geometry. So they needed the exposure to the geometry in order to show this ability to pick up the geometric cue. So my second conclusion is that there isn't any evidence for the geometric module. Language isn't necessary. Features are used in larger spaces. I don't have time to tell you why size is important. Just briefly, it's because you can move around. It's because the cues are more distal, which is important. And it's also because the geometry in the smaller space is easier to see. It's easier to compare the 2 lengths of the walls in the smaller space. There's also a continuing debate about whether features are used in a purely associative way. Liz thinks they are. I think they're not. There's the reference. You know, you can follow this. And there's an overview. But in the time that remains, what I want to go on to is the idea that we can have starting points that are experience expectant coupled with this mature state. The usual proponent of theories in this lower left corner is Jean Piaget. And there are many reasons, which I won't go into, why Piaget's theory, both of development in general and spatial development in specific, is not correct in many ways. But I think there are some ways in which the essential ideas of Piaget actually have merit. And in fact, in a book edited by Scott Johnson called Neo-Constructivism, there has been gathered various arguments for this kind of perspective that I think are very, very interesting. So in the spatial domain, the book, Making Space, that Helene alluded to, has developed this argument, and we've continued to develop it, and other people have worked on it over the decades since we wrote the book. The idea is that the weighting of various kinds of cues, whether they're geometric or featural or response learning or all the different kinds of cues, develops. And there's some recent references on how much babies use visual versus vestibular information. There's a wonderful paper, I think, by Marco Nardini on how integration develops during childhood. So in my mind, the ability to select and/or integrate these different kind of cues is where really the developmental action is. So I just wanted to mention what I meant, exemplify some ways in which I think the starting points are strong. So, I'm not a blank slater. Nobody is a John Lockean anymore. This is work that I did with Jane Ellen Huttenlocher a long time ago, looking at whether children can remember where things are in a long, thin sandbox. Children as young as 18 months will look for hidden objects. If they were perfectly correct, the points would fall along that line. They fall along that line. They know where the toys are. So they're showing metric coding really early. We then moved to do looking time experiments with infants who, of course, can't crawl, can't grasp, but they're looking at things going into and out of sandboxes and then unexpectedly coming out of a location where they weren't buried. That's a metric violation because it's both within the sandbox. And the babies look more when that happens, like, whoa, it didn't go in there, it went in over here. So there's this ability to do metric coding that is present early, and that I don't think you could, teach, and that I think, if I had more time, I could tell you about some of the possible neural instantiations of that. There's also hierarchical combination. I talked earlier about the integration of the categorical and the metric, and even our toddlers looking for the toys hidden in the long, thin sandbox. If they didn't quite remember where it was, I've now turned this, this is the diagonal graph I showed you earlier, but regraphed so as to accentuate the errors. And everything on the left half moves a little towards the center, everything in the right half moves a little towards the center, because the category is in the box. So they're using this categorical combination. Yet, there's developmental change. And I just wanted to tell you about two kinds of developmental change. One is in hierarchical combinations. So the left is what I showed you a minute ago. The right is what you do when you're 10 years old or when you're an adult. You divide this long, thin sandbox into two. It's the left half, and if I have to adjust, I'll squish towards the center of the left half. And if I have to adjust, I'll squish towards the center of the right half. And as you can see from the deviations, you're a lot more accurate when you divide it into two categories rather than in one category. So yes, there are strong starts, but there's developmental change. There's also developmental change in place learning. So getting back to what I said was the most powerful system of spatial coding, those of you who do work with animals know that the sort of gold standard assessment of place learning is tossing rodents into milky water in circular bins and having them swim around to find hidden platforms. And whether or not they can use distal landmarks to find that hidden platform is the key to place learning. What we did not do is throw children into water. That would be even worse than having them look for food. instead what we did, this is actually in a pool, but we didn't put water in it. We put these tiles, and under the tiles, under one of the tiles, is one of these wooden puzzles that you can put, you know, a horse fits in, and a cow fits in, and a pig fits in. And you can't feel it when it's hidden, and you can't see it when it's hidden, because it's really cushy carpet. So the question is whether when you enter from different bits of the pool, holding the pig, and your task is to take the pig to his home, can you find the pig's home? And it turns out that children at 16 to 18 or 19 to 21 months are abysmal at this, and after 21 months, they get much, much better. This has been found previously, although I think not with quite this kind of paradigm, and the question is why? One possibility is hippocampal maturation, so these are some curves that speak to the rapidity of hippocampal change in the first 2 years of life. Another, and not mutually exclusive possibility, is that it has to do with the view from upright walking. So this comes from Karen Adolph's lab. She has kids walking or crawling with head-mounted cameras, so you can see what they see. The view at the left is what we think they see when they walk down this sort of, you know, runway, and the view at the top right is what they see if they crawl, which is pretty much nothing. They just see the runway, because you're looking down when you crawl, right? You can't see anything. Once you get to walk upright, you see at least something of the surrounding environment. So the ability to use distal cues obviously depends on the ability to see them. So upright walking may play a role here, and there may be some kind of reciprocal relationship even, who knows, between hippocampal maturation and the view from upright walking. So there's a lot still to be done. It's hardly, you know, the end of the story, but I want to argue for a position that incorporates both strong starting points of a certain kind and also developmental change. I think this is true of many spatial skills. It's true of mental rotation and paper folding and cross-sectioning and perspective taking and scaling and transferring 3D to 2D representations and back. And if I had a whole week and had you captive in my class, I'd tell you about all of them. But I don't. So there's many more cognitive domains, but I just want to leave you with the idea that a neo-constructivist approach to development in this domain and in other domains, I think, is a very viable approach to thinking about development. So, thank you.
If you have questions, I'm sure Professor Newcombe will be happy to talk with you at the reception. And thank you so much for getting this year's meeting off to a wonderful start. Thank you.